Good afternoon, everybody. I think we're about ready to get started. So if anybody's outside waiting to come on in, please come in and take a seat. I am Krista Walton. I'm the Associate Dean for Research and Innovation in the College of Engineering, and it's a real honor to be here this afternoon to introduce the PRITCHETT Lecture. So the BRUMLEY D. PRITCHETT Lecture Series was established in the School of Polymer, Textile, and Fiber Engineering, which is now Materials Science and Engineering, in 2006 as a memorial to the late Colonel Brumley D. Pritchett. It is the school's most prestigious annual lecture. Colonel Pritchett received his bachelor's degree in textile engineering from the Georgia Institute of Technology in 1930, graduating with an award for superior achievement in his major. While at Georgia Tech, he was instrumental in the founding of the Phi Psi Textile Honors Fraternity and was a member of Phi Sigma Kappa. After graduation, he worked briefly with Dundee Mills before assuming management duties at Eagle and Phoenix Mills in Columbus, Georgia. He joined the United States Army in 1940 and served in the Pacific during World War II. Upon leaving the Army, he returned to Eagle and Phoenix Mills as a superintendent. Later, he joined Steel Heddle Manufacturing Company as a sales engineer and consultant, retiring in 1972. He was elected to membership in the College of Engineering Hall of Fame of Georgia Tech in 2002. And we're pleased this afternoon to have the Pritchett family, son Dan and granddaughter Audrey, sitting right here in the front. So thank you for being here today. And so now I'd like to shift to introduce our guest lecturer. Dr. Laura Greene is a member of the President's Council of Advisors on Science and Technology and is the Marie Krafft Professor of Physics at Florida State University, in addition to being the Chief Scientist for the National High Magnetic Field Laboratory at Florida State University in Tallahassee. Dr. Greene's research is on quantum materials, focusing on fundamental studies utilizing novel materials growth with planar tunneling and point contact electron spectroscopies to elucidate the mechanisms of unconventional superconductivity. Here, got all of that out. Dr. Greene plays an active leadership role in numerous science organizations. In 2017, as president of the American Physical Society, the APS, presidential theme was science diplomacy on national and international scales and its application to human rights. She's currently on the board of directors for the American Association for the Advancement of Science, that's AAAS, and is a vice president of the International Union of Pure and Applied Physics. Dr. Greene is a member of the National Academy of Sciences and the American Academy of Arts and Sciences, and is a founding member of the Florida Academy of Science, Engineering, and Medicine. She is also a fellow of the Institute of Physics in the UK, and AAAS and APS. She's been a Guggenheim Fellow and was awarded the E.O. Lawrence Award for Materials Research from the U.S. Department of Energy, the APS Maria Geppert-Meyer Award, the Belko Award of Excellence, the 5 Sigma Physicist Award for Advocacy and Science Policy from the APS, and the Tallahassee Scientific Society Gold Medal. She has co-authored over 200 publications and presented over 600 invited talks. So Dr. Greene, it's a pleasure to have you with us. Please join me in welcoming her.
keep saying I'm old enough to be his grandmother, so we're just fine. So anyhow, the next one is this analogy that I came up with a while ago, which is the dark energy of quantum materials. And I hope you enjoy it as much as I do. And some people have actually run with it. If I can talk about my work, fine. Otherwise, you're going to have to invite me back for a seminar. So the bottom line is there's many fundamental questions, and we have great progress and promise. Now, I found this on the web because I can find pictures on the web too. Caution, analogies ahead. There's going to be several analogies in here. And I want to remind you that we need analogies to study quantum mechanics. You cannot see, a wavelength of a human being. It's all been testing, and you make up analogies to try to prove yourself wrong or right. And I just want to remind you that what is this here? One of the great minds of the 20th century was Niels Bohr. He came up with the Bohr model of the atom. We all teach it, we love it, it makes sense, and it's completely wrong. So keep that in mind when you're doing these things. Okay. So the National High Magnetic Field Laboratory, we have 3 campuses. The main campus is in Tallahassee. It's not that far. Come on down. And it's a large building. When I go from my office to my laboratory, my Apple Watch starts closing rings on me. And so we have 7 user facilities. 4 of them are in Tallahassee. So here's where Tallahassee is, not too far from here. And the 2 most famous ones we have here are, we have a 45, the strongest magnet in the world that's DC, that's continuous. It's 45 Tesla. And we also have the highest NMR magnet in the world, 21 Tesla, 900 megahertz. And there's 2 other user facilities that I will mention during the beginning of my talk. In University of Florida, we have 2 interesting user facilities. One that I won't have time to talk about is the high B over T facility. It's not as high B, not as low T, but the ratio is very high, and there's a lot of very important fundamental physics that's done there. And those experiments often go on for months at a time. And then I will mention a few examples of our advanced magnetic resonance imaging and spectroscopy facility, where we do magnetic resonance imaging as high as 21 Tesla. Finally, in Los Alamos, we have our pulse field facility. And I like to show this picture of our generator. And that's a normal size human. If you can get out to right now it's being worked on by GE. That's the way it goes. But it will be back up and running again shortly. But if you ever get a chance to see this generator, it's pretty amazing. It was bought from the Tennessee Valley Authority. Now, I'm not going to go over the mission, but I want to point out one thing because it came up in the discussion last night. Since we are an NSF laboratory and primarily a user facility, this is basically our mission. Be a user facility, be out in front, do good research so you get good users coming in. But one of the main platforms is education and outreach. That's not true in other national laboratories. I won't have time to talk about it now, but if you want to look at Sci Girls, Magnet Academy, et cetera, we have hundreds and thousands of hits every few months. So I recommend you take a look at this stuff. It's really pretty neat. And here's some facilities below, but I wanted to point out our latest, greatest hits. I'll just point out a couple of them. This is a 32 Tesla all superconducting magnet. The strongest all superconducting magnet that I know of right now is 20 Tesla. And every time you go up a Tesla, it gets harder. And this is actually a user facility. And it's an amazing accomplishment. And because we were able to this and the little test magnet that's all superconducting that went to over 45 Tesla, the National Science Foundation just gave us funds for a new, instead of 32 Tesla, 40 Tesla magnet, and for the design phase. So it's all very exciting. Now here's our Delta Airlines map of the National Magnet Lab. So we can see that people come from all over the country, and we can see where the Delta Airlines hubs are. So that's Los Alamos, Tallahassee, and Gainesville. And we get users from all over the country. I'm using 2019 statistics because of the pandemic. It looks better. But we're actually back up again, except for some challenges in helium. We're back into full running. But we have over 2,000 users a year, almost 200 institutions, and they come from all over the world. Some of these, there's about 10 magnet labs in the world, and since we have the best magnets, the best probes, it's everything, they come from all over the world to come to our magnet lab. So 300 institutions around the world. Newcomers are welcome. This is my advertisement. So you go online, you write a short proposal, and if you don't know what you're doing, contact one of the Mag Lab scientists. You can find them all online. They'll help you with it. If you get funded, the user time is free. As long as it's publishable material, it's free. You just have to get there. I have a big house. You can stay with me. And so, and I want to point out that depending on the user facility, 25 to 35% of the PIs are first-time users. So we know how to train people how to use the magnets. Don't worry if you haven't used them before. And then people ask for the bang for the buck. And if you divvy the magnet lab up into single investigator grants, you wouldn't get as many publications in high impact journals. Okay, you don't need the numbers, but you get that. There's 3 major mag lab research themes. There's materials, energy, and life. So the materials one, I'll talk about this dome later on if I don't run out of time. I'm going to talk a little bit more about materials, a little bit of energy, and some of our life that we do in our research, just to give you a feel for it. This is something that's fairly new. It was actually published in 2019, but it started a whole new field. And this is a kind of interesting material called the heavy-fermion. And there was a whole new kind of superconductor that was discovered. We call it the Lazarus superconductor because it wakes up after a while of magnetism. So at low temperature, this blue area says it's superconducting. And this is all done at low temperature. As you raise the magnetic field this way, and I'll mention a little bit, too much magnetic field kills the superconductivity. But then something happens at a certain angle. This is 35 Tesla. So this is something like 700 times, about 500 times the size of the permanent magnet on your refrigerator, okay? And all of a sudden, the superconductivity turns on again. And it looks like, for the experts here, there's a good chance it's a triplet. We don't know for sure yet, but it's polarized, and it looks like it could be a triplet superconductor. Now, I don't expect to run a qubit at 35 to 60 Tesla, and that's where it's superconducting, but, this might be an interesting material. Another one that we've looked at, and I'm bringing this up for the QIS people here, and this is done in our, oh, by the way, this one was here done in 2 facilities, the DC facility in Tallahassee and the Pulse facility in Los Alamos. We have an electron magnetic resonance facility, which is sort of like far infrared spectroscopy in a high field that Steve Hill runs. So this was one of the, there's many, I'm just picking out a few exciting things here. This hasn't been done with an anti-ferromagnet before. You have an anti-ferromagnetic material, you hit it with terahertz radiation, and you can have polarized spins going into a weakly diamatic material, and you can pull off the different orientations. And so this looks like it's promising other spintronics applications. If you want any more information, I can send you it, but I have to do an overview. This is what physicists don't know about. This is ion cyclotron resonance, also called Fourier transform ion cyclotron resonance. When no one in the world can come even close to this resolution of mass spectrometry. So it's done at 21 Tesla, and basically you spit in, it was developed for oil. Oil is the most complex fluid on the planet. You put in a spit of oil at 21 Tesla, so it makes it cyclotron frequency, you chirp it with a laser, and you get a spread of masses. And as of the last 2 years, we now can get the mass difference to about 1 electron. Okay, so it's like a mass spectrometer on ultra steroids. And why do you want to do that? So here's 3 reasons you want to do it. It was developed for petroleomics. Exxon and BP both dig wells in the Gulf. They want to know if they hit the same reserve, right? And we can tell them, we can fingerprint that enough that we can tell exactly. So they come to us, they can't publish, so they pay for their user time. Another example is if there's an oil spill. We can do forensics and tell exactly what oil head it came from. We are that accurate at it. And for proteinomics, so this is done where you can look at proteins. It's so good at this is not even working. So there we go. So the mass is so accurate that we can actually tell in some materials the protein folding. So you take something like the P54 protein. As many of you know, the protein's folding determine what its properties are, and so what happened to the P53, you can do a hydrogen deuterium transfer and determine the protein folding and determine protein makeups. I'm going to have a couple of slides on climate change and sustainability. The second most complex fluid on the planet is dissolved organic carbon. And so I'll show you some examples of that, and classifying carbon in the permafrost, and plastic and the forever chemicals PFAS breakdown. So first of all, there's a lot of experiments where they go into the Arctic and they measure as a function of time. They just pick up liquid and they do this, and they can measure how global warming is changing in the Arctic. This is one that is also very exciting. So when you have runoff of asphalt in the built planet, you want to know, is it going to be water insoluble tar or is it water soluble? It has tremendous impact on the environment, and and no one can tell that except the magnet lab. So these are almost identical examples of carbon, dissolved carbon, and just they're so slightly different in mass that you can tell whether it's dissolved or not dissolved carbon. And here's an example of some of the data here. That difference here is 1.0 in electron mass difference. I wanted to throw this in. This just came out a couple of months ago. And we thought that the plastic bags from Walmart, CVS or whatever, were forever chemicals PFAS, which is bad. They're not healthy, but we thought they were forever. Work done at the Magnet Lab, published very recently, finds that exposed to sunlight, these plastics can actually break down. And we're trying to determine what they're breaking onto and how dangerous they are for the environment. So a couple examples of life. So MRI goes high definition. So how many people have been into an MRI? Anybody over about 25 has? Okay, yeah. So the best part about MRI is you get to go inside of a superconducting magnet. That's cool. Okay. So, but that's typically 3-4 Tesla. We do MRI at 21 Tesla. Now, the way MRI works is that you line up all the protons on the body, namely the water, and you put a high magnet field on it, and you can see how the protons line up, and you can do a spectroscopy of where the water is in the system. Now, you do the spectroscopy with radio frequency light, and the higher the magnetic field, the higher the frequency, the shorter the wavelength, the better the resolution. You go from 4 Tesla to 21 Tesla, you go from measuring things on the order of a millimeter to things on the order of microns. Okay, but it is not that healthy. So it's not as bad as being in a microwave oven. You can do it on living things, but you want to be very careful, and it's not quite commercial yet. So we're doing some prototypes on that. One of the examples is this here. So at 21 Tesla, as I mentioned, you have higher resolution. No one can detect plaque amyloids earlier than we can, and it's simply a resolution problem. So the plan is, if this goes past prototype, is that if someone starts having, they feel like they might be getting, Alzheimer's, something like that, change of taste, change of smell, things that happen, you can actually, hoping we can check and look for plaque amyloid detection very, very early. The reason it measures liquid. So the plaque amyloids cause microhemorrhages, and that's what MRI can pick up. Finally, this is one of my favorite examples. This has been around for a while. We have unlocked the periodic table. When you go get an MRI, it's done on water. It's done on the protons. Let's look at something else. There's many elements that we look at. This is an example of looking at sodium. Why are we looking at sodium? So here we have, by the way, this is sodium imaging in a mouse brain. Sodium is much heavier than a proton. So you don't need as high an RF frequency. And so the resolution is lower, but you're picking up specifically the sodium. It turns out that when cells are dying, they uptake sodium. We don't know exactly why. We have a good idea, but it doesn't matter. That's how a lot of cancer research is, and a lot of research. When cells are dying, they uptake sodium. And after I got to the Magnet Lab, you can actually buy a rat with brain cancer. I didn't know that. So here's imaging of a tumor only looking at the sodium. Mostly looking at the sodium. And you image that sodium, and you give the rat chemotherapy, you wait 4 days, and you image again. Nothing happens, you try a different regime of chemotherapy. Repeat, repeat. At some point, if the tumor lights up, that means there's an accumulation of sodium. That means there's a likelihood that the cells are dying, and you have a chance that that chemotherapy may be successful. So this is very, very promising, but needs to be scaled up. Okay, enough of the Magnet Lab. So now you've all seen talks on high energy physics, right? And in every high energy physics talk, they have to show the ring. I don't know why. So every low temperature physics talk, we have to show this graph. So this was the discovery of superconductivity in 1911 by Heike Camillus-Onnes. He and Giles House, out of serendipitous questions, said, what happens if I cool down a metal? And there were predictions, like if you cool down the metal, it'll become resistive. So this is resistance versus temperature. You're cooling it down. People didn't know what would happen. There were guesses. It turns out that the resistance dropped abruptly to zero. Bam. Now, for those of you that are experimentalists, it took years to prove it was zero, right? You could measure something small, but to actually prove it was zero was a very interesting science that went on for a while. And they also, Camillus-Onnes, and by the way, Giles House wasn't on the paper. He didn't win the Nobel Prize, but he also went on to start Philips. So I think he did okay. So they also discovered that not only do you have to be below a certain temperature where the resistance is zero, but if you put too much current through it, it's not superconducting anymore. If you put too much field on it, magnetic field on it, it's not superconducting anymore. So all these things will destroy superconductivity. Now, I'm going to do this very quickly. I'm not going to give you a lecture on superconductivity. I just have to tell you that we do understand a lot about superconductors. There are probably 3 quantum materials questions out of hundreds maybe that are solved. This is one of them, okay? And it's an amazing story. I could go on for hours about it, but let's consider what they figured out was that a superconductor, they figured out early on, has long-range quantum mechanical order. So if we think about conduction into a metal, if this is a metal and there's conduction going on here, all the electrons are bouncing around and conducting. What happens in a superconductor is that all the electrons fall into a single quantum state, and they move along without any resistance at all. And that was a hard thing to figure out. So instead of needing 10 to the 26 equations for electrons in a metal, you need one equation. And that's a superconductor. Now, I don't know if you know this, but many of you do and many of you don't. There are things about certain atomic particles. It's called spin. Spin is its magnetic moment. It doesn't mean it's spinning, it's its magnetic moment. Electrons have spin 1/2. Okay? Anything that's spin 1/2 is called a fermion. Thank you, Enrico Fermi. And that means, without having to know why, it's correct that no 2 fermions can occupy the same quantum state at the same time. So how did all these electrons that are fermions fall into a single quantum state? Plus the fact all electrons are negatively charged. You know, Coulomb's law says, no, 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 no. How do you repeal that law? So what happened is this happened at my old place, University of Illinois, and it was, remember, it was discovered in 1911. In 1957, the theory came out and it solved it. Bardeen, Cooper, and Schrieffer came up with a microscopic theory of superconductivity, and that there's long-range interactions between electrons, and they pair into something called Cooper pairs. That's not real space pairing. And without going into details, what we have here is that you have a background lattice, maybe niobium, and at low enough temperatures, an electron goes through, and if there's a strong electron lattice, electron background interaction, it can distort the lattice, and another electron sees a positive wake and gets pulled in. That analogy breaks down pretty quickly. But what we do know is that this is completely solved. We can predict everything about these. Electrons are paired in this complicated distant pairing dance, and it's due to the phonons or the lattice interactions. Solved problem. But they didn't have anything. Everyone thought, by the way, Camillus-Onnes came to Chicago in like 1913 and said, superconductivity will solve the energy crisis and cure cancer, and who knows what else. But they didn't have any practical applications until John Hume in 1952 invented these other materials that have a higher TC, which means the superconducting transition temperature. And to date, all superconductors need to be cooled, but they also can stand in stronger fields. So before this, they weren't practical. So when you go into an MRI machine, they need to put a lot of current in there. And if you use something like lead or what we call a type 1 superconductor, it won't stay superconducting if you put a lot of current in it. So they had to invent all these interesting superconductors. So So he invented this thing called niobium-3 tin, which is hard to work with, stiff, hard to form. We make magnets out of it, but it's difficult to work with. But I'll have a slide about CERN in a few minutes that shows how it's interesting again. Then in 1963, he made the first practical wires. So niobium-3 tin is a compound, so it's not malleable. Niobium titanium is a random alloy, so it's reliable. So it's the standard in the field. So whether you're talking about CERN or the ITER project to try to make fusion in southern France, or MRIs, or whatever is superconducting, niobium titanium is the superconducting standard. Now, this is the fun part. Do we have time? Yeah, so we're going to have just a little fun thing right now. So type 2 superconductors, all practical, it's two kinds of superconductors, type 1 and type, anyhow. So type 2 superconductors just mean that they could maintain a high magnetic field. So remember I told you that high magnetic fields kill the superconductivity. What happens in a type 2 superconductor is they allow some penetration of magnetic field into the superconductor. Okay? This is really important for application. So here's a cross-sectional view here. So this blue part here is the superconductor, and these lines are lines of magnetic field that can go through the superconductor. And then you get these vortices of Cooper pairs that go around it and shield the rest of the superconductor. One of the things that I study for applications, especially in the high temperature superconductors, is you need to pin these vortices. These are vortices, these super electrons going around, because the inside of these vortices are normal metal, and if they're allowed to move, they will dissipate energy. Okay, got it? Now we get some fun. Okay, so Matthew said it was an amazing production, and they do switch the cups at one point, and I've looked at this enough times and I can't see when. But they switch the cup, so he had this magnetic track, and then the cup then has a high temperature superconductor in the bottom and liquid nitrogen in the top. So I still haven't, they're good. So I just want show you a couple of applications, just two of them. There's many, many more. One of them is relevant to today. And that is that we've discussed for years until, gosh, when did this crashed around 2006. You may know that this happened recently, this past winter, there are actually 3 separate power grids in the United States. And the power grids are AC because Mr. Tesla won over Mr. Edison, the alternating current. And as many of you know, if you connect alternating current circuits, if they're not matched up in phase, you lose a lot of power. So right now we have 3 grids. We have the Western interconnection, the Eastern interconnection, and the Texas interconnection. How do we connect? We all know this from anyhow. So how do we connect them? So there was something called the Trans-Omega Superstation that the DOE was going to fund, but then they cut the funding, and private industry tried to do it, but I think this should be on the table again. So there's a place in Clovis, New Mexico, where the 3 grids meet, and what you would do is take the AC power from the Eastern Interconnect, convert it down to, convert it to DC, use big superconducting cables, and then you get to the next grid and you invert it back to AC, and you can have seamless connection of power across the United States. That would be important, but I hope they do it. But here's the other one that's fun, and that is when Fabio Giannotti, who is the Director General of CERN, gives a talk, the Mag Lab is all over it. So this is one of her slides, which I've changed a lot, from a AAAS plenary talk in 2019. And right now they're working on the high luminosity upgrade of the linear, of the LHC. And with help from discovery from the Magnet Lab, they're actually going to, we've made niobium-3 tin a little bit better in that it's being used for the high luminosity upgrade. And it's hope we also have this new material, hafnium doping, that we think has a good chance of being used in the next large machine, the Future Circular Collider. That would be very exciting. But she's always telling us, you give us the magnets, we'll get to the next energy. So that's conventional superconductivity. That's one of the solved problems in correlated materials. What I'm going to do with the rest of the talk is tell you a little bit, just a little bit, about unconventional superconductivity and why it's so interesting. So Franz Douglas in 1979 discovered superconductivity in a very strange material. They're called heavy-fermions. I've been studying them for years. It turns out, heavy-fermions or electrons or fermions, that if you measure the electron mass, and you could measure the electron mass inside of a solid by doing thermodynamic measurements like heat transport, okay? And you can look at all these together, and the mass of the electron is outrageously large. For those of you that have had solid state or condensed matter physics, you know that the mass of an electron is determined by what's in the material and where they sit, right? The band, how tightly the band is bent, okay? That gives you the mass. This doesn't work. There's something else going on here. And this begins the beginning of what my definition of quantum materials are. And there's many, let me just say my definition of unsolved quantum materials, because actually everything's a quantum material, but what are you going to do? Okay, so, but we like the title, it gets, you know. So this is something that, there's something called a Fermi liquid or a conventional metal. And we can tell you all about I'm going to say this a couple of times. We can tell you the optical, thermodynamic, and transport properties of these simple metals by knowing what makes up the lattice and where they sit in the lattice. Electronic structure calculations. One of my definitions of quantum materials is it just doesn't work. It means the electron-electron correlations are much more important than the electron lattice correlations. Interactions, okay? So this is one of the first examples when I was growing thin films of a material called serum copper 6 that had 1,000 times the free electron mass. That was a hoot. So anyhow, what we found out is a couple of things here. One is there's magnetism in these materials. Remember I told you too much magnetic field kills things? You need magnetism in these materials. And what happened in these discoveries is that electron-phonon BCS theory of superconductivity, the microscopic theory of conventional superconductivity doesn't hold. Okay, so we got to figure this one out. And Gil Andras, a good friend of mine, discovered this first domed phase diagram. I'm going to show you a few of these. So on the y-axis is temperature, and on the x-axis is some thermodynamic variable, in this case, pressure. Okay, I often do it by changing the components in the material, like putting another material here, so changing the number of carriers. But what we have here is AF means anti-ferromagnetic. I showed you an anti-ferromagnet earlier. This is something that has magnetism in it. And on this side here is a Fermi liquid, a simple metal. And so you have a phase transition between the magnetic and the normal metal. And when you go down in temperature and you want to see what's happening at zero temperature, superconductivity appears. Yeah, we don't know why. Okay, so, but there's a lot of theories, and I'm happy to talk about any of those. This is an incomplete plot. There are at least 50 conventional superconductors. I just showed you one. That was the one that I showed you here. And if you go up here, these are the heavy-fermion superconductors. Everything in red here is what we understand. Everything in red is one of these conventional BCS electron-phonon coupled superconducting. Nothing else is like that. Here's the famous high-temperature superconductors you've looked at. Here's the iron-doped superconductors. Here's, well, actually the hydrogen, the ones that we can verify, look like they're conventional superconductors. I showed you that dome. Here's a figure here, and I'm just going to blow up that figure. Here's another dome. It's just a little more complicated. What we have is temperature going up and down here, and a thermodynamic variable here, either pressure or changing the components in the material to make more or less carriers. And what we find is typically it's anti-ferromagnetic on this side, a simple metal on this side, and as you lower the temperature, you get a superconductor. These are not conventional superconductors, but I want to tell you my definition, okay? Now here we kind of understand these anti-ferromagnetic insulators, and we certainly understand Fermi liquids, okay? And I submit that we do understand a lot about superconductors. Even though we know that those like heavy fermions and high temperature superconductors aren't paired only by electron-phonons, they're still, to our knowledge, everyone that we've measured are still Cooper pairs. So we have an equation. You've heard of the Schrodinger equation? That works for normal metals. What we have for superconductors are the Bernoulli-above-de Gennes equations. It's like two Schrodinger equations, one for electrons, one for holes, an extra cross term for the electrons and holes, so it's a little harder to solve. But if you put your mind to it, it's a little more complicated. You can really solve the microscopic properties of any superconductor. You have a question? Millions of measurements. Like, yeah, Josephson measurements, for instance. Okay, where you actually measure pair transport. Yeah. So, yeah, actually, the very early days of a high-temperature superconductor, a theorist friend of mine came out with a paper that said they weren't paired, and he was completely wrong, but we all loved him for having the courage to publish that paper, and he had all this theory about why. You know that story where someone says, here, let me show you this data. Oh, I can explain that. Oh, wait a minute, I gave it to you upside down. Oh, I can explain that too. So, gotta love them, theorists. Okay, so anyhow, what we have up here in this funny area above the superconductivity before it becomes superconducting is one of my definitions of unsolved quantum matter. It's just weird stuff, things that go bump in the night, whatever you want to say. And I'm just going to give you an overview. Here are examples of dome phase diagrams. Here's the one that I showed you. This is high temperature superconductor, the cuprates. Here's some one-dimensional. It's an organic superconductor. This is something called the dichalcogenide. There's just lots and lots of families. I've worked a lot on these two materials, which are the newer iron-based high-temperature superconductors. When those came out, I said, whoa, iron-based superconductor? Obviously not electron-phonon. Something's going on here. So we do know a lot about these. So now just a little bit of a flavor, and then the analogies, and then this is, again, a flavor. So what we have in these areas above the superconducting phase, in between the magnetic and the normal metal phase, and by the way, they don't all have these phase diagrams. They almost all have these phase diagrams because nothing in quantum mechanics is absolute. There's always exceptions, and everything's a little bit buzzed out, so just keep that in mind. So what do we have here? There's something that I studied a lot of, and these are data from my group here. It's called electron nematicity. So in this particular material, if you look at a high temperature and you look down on the lattice looks square. Okay, so up here, the lattice is square in this whole white area. When you go down in temperature, for reasons that are still being discussed, the electrons break the symmetry. They are no longer have the square symmetry, but they form these, little sausage-shaped things here, or cigar, depending on what you like, but they form these little things. And so the electron fluid, we call it has C2 symmetry because it can flip it around 180 degrees, has a broken symmetry from the underlying lattice, which is C4 symmetry. You can't explain that with simple Fermi liquid theory. I mentioned the heavy electrons. There's something called stripes, where the electrons just line up in stripes. And in some cases, it looks like the spin and charge may be separated. There's something called the pseudo gap in the cuprates. In transition metal oxides, you get these charge density waves that have temperature dependencies that you can't explain, and other kinds of things. So what I have found, what seems to be true, is that all these unconventional superconductors have in the electron fluid above the superconducting state, the electron fluid breaks the symmetry of the underlying lattice. It has a lower symmetry than the underlying lattice. So like I said, those are my measurements. Now, this is the kind of overview that is going to lead to the analogy. So this is a mishmash. When someone says, what's the big question in quantum materials? I said, we have no Higgs boson. We have no gravity wave. What we have, and I've been in this business a long time, is I have seen the number of kinds of measurements grow. This thing here is done at the magnet lab. These are called quantum oscillations. You can see how the electrons move on their Fermi surfaces, get the mass of the electrons, the shape of the Fermi, et cetera, et cetera. These are some of my measurements here. There's all kinds of measurements that we could do: planar tunneling, point contact, ultra-sensitive transport optical properties, scanning tunneling microscopy, resonant inelastic X-ray spectroscopy, and we put these all together to try to understand what's going on. And we agree and disagree, but it's really interesting. But also, besides those measurement techniques, what happens on a few-month basis is that materials quality is increasing. So I'm going to show you, if I have time, I'll show you a snapshot of a couple materials that I would say even 2 years ago weren't possible. So the quality of growth has completely changed. Finally, the computation has completely changed. So what we have developed in the last few years is developed a whole suite of measurement, growth, and computation to look at this suite of quantum materials. So it's actually pretty complicated. So I'm going to get to the analogy. I think I have a couple more minutes. So what I call solved is a Fermi liquid, okay? And I explained why. General electronic structure works well. Superconductors, we understand them, okay? And there's a few other things. There's the quantized Hall effect and simple magnetism. General definitions for unsolved quantum matter. The electronic properties can't be described by the crystal structure and the component atoms. And the experiment is that the electron-electron interaction, we could measure this, is the electron fluid is just different than we can predict than we expect to measure from the lattice. So here's pictures of that. So we know this is the definition of a Fermi liquid, which is you have a big bucket. This is the simplest one. And remember that the electrons all can't go to the same quantum state. So you throw in the electrons and they fill up to a certain level. We understand that. And we also understand Cooper pairs in the superconductor. These are solved questions. They're just solved. Now let's go on to this. In unconventional superconductors, the far right side of the diagram, we understand. We understand what's going on. We can model what's going on in the superconducting state. But above here in the quantum matter state, we can. And I have my little favorite pneumatic electrons pumping together as that picture. So solved, we can model it, and there are many, many, and they're all slightly different. Caution analogies ahead. So I'm going to finish in a second. Okay, how am I doing? So I was at the Kavli, the 2016, when Kavli gave Kip Thorne, Rainer Weiss, and Barry Barish the prize for the Kavli for discovering LIGO, for discovering gravitational waves. And what happened was Kip Thorne put up this picture. And because I was on one of the committees, I got to talk with him a few times. I've met him a few times. He's really interesting. And you may have seen this before, but this is a two-dimensional representation or 2 or 3 dimensional representation of a 4-dimensional space-time continuum. So the way we represent this is that we have the sun here, and the sun is very massive, and it causes a big depression in the space-time continuum. And here's the Earth there, and it's a little weaker, and it doesn't distort the space-time continuum quite as much. And I saw that, and I thought, distortion of the background. Can I compare that to BCS? So I walked out at the coffee break, and I told it to some of my friends, and they decided I was certifiably insane. But 56 hours later, flying back from Norway to Denver, I finally got the analogy. So here's the analogy, which I think is worth, and other people have taken it further along with the mathematics, which I can't do. Okay. Gravity wave detector LIGO. How many people have heard of that? Okay. The best $1 billion the NSF ever spent over 20 years. Okay. It really is. I mean, it was predicted, and they had to see it, and they did. And the whole history of that is amazing. Why is this so amazing? Remember, there's this giant interferometer, and they're measuring the distortion of a mirror that's less than the width of a proton. That's what they measured. But the energy was more than the combined power of light radiated by all of the stars in the observable universe. What's wrong here? We're not measuring photons. We're not measuring mass. For the first time, we're measuring something completely different, gravity waves. So for the first time, we have a whole new telescope or microscope to put on the planet. Pretty cool, right? So this was amazing. Okay, so what we have now for quantum materials is many quantum detectors. Our better crystal growth, our better measurement, our better computation. So what happened in gravity? Newton came up with this idea that worked pretty well. 1 over r squared, m1, m2 over r squared. It worked really, really well, except it was immediate action at a distance. So Mr. Einstein came along, because he was Mr. Einstein, and he said, there's some problems here. Immediate action at a distance, and some of you know the history, the retrogradation of the perihelion of Mercury. There are a few things that didn't work. And he came up with this whole theory of general relativity, that the fundamental microscopic theory of gravity was this general theory of relativity, which is the distortion of the space-time continuum. The question that's put forth by people in this field is that they weren't just looking for gravity waves. Can this new way to look at the universe help us understand some of the greatest unsolved problems in physics, which are what the heck are dark energy and dark matter? We can say the same thing in quantum matter, which is Mr. Fermi showed us how to look at a simple metal. And then Bardeen, Cooper, and Schrieffer, with the experimental help from Kamerlikonis and many, many other people, said, this doesn't quite work here. And they came up with one of the explanations for a non-Fermi liquid. But now we have many, many quantum materials that we can't answer. Taking the analogy one more step before I'm going to finish. Okay, Newtonian classical gravity. Gravity is determined by the forces between objects derived from their mass and their position. And that's true in simple metals. The properties of the simple metals are derived from the crystal atoms and their positions. For the Einstein general theory of relativity, masses create distortions in the space-time continuum. In the BCS theory of superconductivity, electrons create distortions in the background crystal lattice. And that's just one of many, many, many quantum materials. Will LIGO help us understand these questions? Will our suite of quantum telescopes help us understand many of our suites of quantum materials? So I have to flash this. Maybe I'll just show one. This is a fairly recent measurement. It's showing that, although we still have to do a film, we didn't only got through PhysRev B, but I'm convinced that we've shown that the pairing mechanism in this particular material, not only is it not electron-phonon, it's paired because the electrons are scattering off of the F electron. This is cerium cobalt indium 5, and that means it's got cerium in it. Okay, and we have shown that it's this new pairing mechanism. And just to show you some data, at low temperature and planar tunneling, you see the superconducting properties. If you go way above where you're not superconducting anymore, you get a whole different feature. It's a field-induced gap, and moving on there. And an experiment that's in progress. I had to throw this in. It's not published yet, but for those doing QIS, is that we're growing we're growing a condo insulator that is probably topological on top of a simple conventional superconductor. And we're trying to look for proximity effects between the simple S-wave superconductor and the topological condo insulator. And we've gotten to the point where we have really good data, and the hope is that we can induce, maybe, topological superconductivity into this superconductor. Finally, many families of unsolved quantum materials. I believe, and we have to have beliefs in this business, that if we can start to really understand all these things, that will help us understand what the next, how do we design a qubit, right? Is it going to be a superconductor? Is it going to be a topological material? Is it going to be a, quantum spin liquid? There are so many things out there. Molecular magnets, right? That's a big one. So we need to understand these things, and there's so many layers. It's very, very exciting and very fundamental. And I think we're at a precipice to really understanding some of these great, exciting things. So thank you very much, and I'm happy to answer questions.